Griffiths E&M section 3.1, Potentials and Uniqueness. So just to recap what we've done so far in this course. The goal in general is to calculate the force at a charge field. All right. We decided to start by looking at the electric fields in all space, knowing that the electric field at a particular point in space and with a charge Q in it will feel some force, right? A Q electric field. Okay. We started off by saying, all right, well, if we want to calculate the electric field at some point in space, we can do this integral over the charge distributions in space right? You integrate over all the charges, where they are, their densities, and you can calculate what this electric field is. All right, and it turns out that that was very difficult to do. So we said, all right, well, you can take advantage of some sort of symmetries, right? So if I have a spherical charge distribution, I can use Gauss's law and spherical coordinates, right? Same with the cylinder, right? You can do another Gaussian surface that's a cylinder, right? And that might be considerably easier if it's possible, but it's not always possible to exploit that kind of symmetry. So we thought, all right, well, maybe instead what we can do is calculate the potential at some point in space, which is still going to be an integral, tends to be a little easier to do, or I'm still integrating over this charge distribution over space. Because this is not a vector, I only have to integrate once, so generally a little easier, and then it turns out that this r squared on the bottom difference, generally creates a little bit easier integral to do. Okay, so that's possible to do. It turns out that that's not always the easiest thing to do either. So there's a new kind of approach that we're going to suggest here, is that instead of trying to take this integral over all space, we can go ahead and write Poisson's equation in differential form right here, where I take the Laplacian of the potential, and that is equal to 1 over epsilon naught times the charge distribution. Okay, so this is now a differential equation that we're solving, as opposed to trying to do an integral. Let's say we have some sort of charge distribution, I don't know, charges here, okay? And we want to know what the potential is in some region of space. And a common choice to do is to say, all right, well, there are charges here, but what if I care about the solution to the potential here, where that container, or that region of space that I care about has nothing, it does not include any charges. All right, if that's the case, then this reduces down to Laplace's equation. All right, so if I want to find the solution to the electric field or the potential in some region of space that doesn't have any charges, I can solve this expression here, which is in general pretty doable. Okay. Just an example, if this were, if I was looking for a solution that might exist in Cartesian coordinates in 3D, I would have some expression. I'm just expanding out this. That is equal to 0, where I'm assuming here that the potential is now a function of x, y, and z. And if I have my potential, then I can go ahead and take the negative gradient of that potential and get the electric field. All right. Now there are many different ways we can do this, and the goal would always be to figure out what's the solution to this differential equation. All right, you can do this in 1 dimension, 2 dimension, 3 dimension, all different kinds of coordinate systems, but in the end, it all comes down to solving these differential equations. Okay. We're not going to be doing a ton of this, but I just wanted to to introduce this topic so that we can talk about the uniqueness theorem in particular. Okay, so the uniqueness theorem says that, all right, my goal is to calculate or find what this potential is. The first uniqueness theorem says that if I know the potential at all of my boundaries of my container, I then know the potential, everywhere inside the volume. Okay, that's why you might have solved problems like this before, where you have all these boundary conditions that you apply, and that gives you the full solution. Okay, the second uniqueness theorem exists. It tells you something about the charge on conductors. But really what I want to focus on is the fact that if you can find a solution for this potential in space, it is the solution. All right. You might say, oh, how do I know that I have the right solution? But if it satisfies this expression and it works, it is the solution, right? And that's going to come in handy in a second. Okay, so instead of trying to solve these integrals for electric fields, we introduced Gauss's law. Sometimes Gauss's law is not applicable due to lack of symmetry, so we solve an easier integral for the potential. Sometimes that's even too hard, and now we're saying, all right, if you can break up your problem and solve these differential equations, you have the ability to guess a solution, and if that solution works, it is the solution.